So, we were talking about Hartley's measure. We talked about that it should be dependent on the size of the sample space. It should be a logarithmic function, so that it correctly captures the uncertainty of compound events. And then we said that one deficiency is that it completely ignores the possibility that different samples in the sample space may have unequal probabilities, in which case it will probably not be a best measure of information. And we showed that that although both had the same 4 number of balls, the information conveyed by taking out one ball was coming out to be same in both the cases, while it should not have been the same. The Shannon measure of information was, so we have already answered this question, what is wrong with Hartley's measure of information. If ith possible value of x has probability pi, then the Hartley information should be weighted by pi to give this amount of information provided by x. This is Shannon's measure. So, the model that Shannon proposed was that we should measure information. So, was that sigma I is equal to 1 to L pi log pi with a minus sign. Minus sign is very easy to understand, because pi is a probability of the ith sample, and this probability will be less than 1, it cannot exceed 1. So, naturally the log will be a negative number. So, that minus minus will become plus, and then pi is always greater than 0. So, this quantity will actually be a positive number. So, sigma minus of pi log pi. So, the essential change is that factor of pi coming, and that will change this scenario completely. The another thing, beautiful thing that this takes care of is what is known as the grouping axiom, that you can write the word grouping axiom, because it is not there in your notes. And let me tell you what that grouping axiom is. So, the grouping axiom says that if I have, say, n possible outcomes x1 to xn, and suppose I divide this into 2 possible sets, say I say set A is say x1 to some xr, and I say set B is xr plus 1 up to xn. So, I am saying that my original sample space is from x1 to xn. I divide this into 2 sets, set A is x1 to xr and set B is xr plus 1 up to xn. So, what the grouping axiom poses is a very interesting question. It says that suppose the original uncertainty associated with this information is some number based on that size of the sample space x1 to xn. So, it will be pi log pi, right, I varying from 1 to n. If instead of being told that what is the outcome from x1 to xn, if you are only told that the outcome is from set A or set B, has your uncertainty reduced or not? Uncertainty has reduced. So, you are not being told what the specific outcome is, you are being told, oh, your outcome is from set A. Now, the uncertainty is only the uncertainty associated with set A. So, I do not have time here, but this expression actually addresses the grouping axiom also. That means that if you are told that it belongs to set A or set B, and what is the uncertainty associated with set A or set B? It is only log 2, because there are only 2 outcomes, either set A or set B. So, if you are told the uncertainty associated with set A or set B with their respective probabilities, and if you subtract this uncertainty from the original uncertainty, then the remaining uncertainty is actually equal to the uncertainty associated with set A or set B. So, something similar to what the independent event example I had given earlier. Shannon's measure of information actually satisfies the requirements of the grouping axiom also. Last property that is there is that whatever measure of information is there, it should be a continuous function of probability. That means, if I plot it, then the mathematical function should be continuous. And again, we do not have time in this 1 hour here, but in this book it is shown that the only function only mathematical function that satisfies all these 4 axioms. Which are the 4 axioms? It should depend on the size of L, it should satisfy the probability of the independent events, that independent events the information should add up, it should satisfy the grouping axiom, and it should be continuous. This is the only function that satisfies pi log pi. Forget the summation part. The measure of information is pi log pi, that means the information associated with event. What is the? Continuous function. There is no other function, mathematical function, which satisfies all the 4 axioms. And that is why I am saying that we often do not realize how profound this simple looking function is, how deep this simple looking function is. It is able to capture all that our intuition is wanting. After all, the axioms are all intuitive. If f is any real valued function, then support of f, we will need this definition of support. Support of f is defined as the subset of its domain where f takes on non-zero values and is denoted by SUPPF. SUPPF means support of f. So, for any function, look at its domain in which it is non-zero. That part of the domain is known as the support of f. Any questions? Yeah. Last ones? Okay. So, what we are saying is that suppose I have a function, right, and this function is like this. Then this is the support of the function, because it is non-zero only here. This is not the support of the function. That part of the domain in which the function is non-zero. And why it is very important in our case, because many times we will define events for which the probability is 0. If the probability is 0, we will exclude it from the support of x. That is why we are defining the support now, we will be using it. The uncertainty or the entropy of a discrete random variable is given by this function. Now, this is a straightforward expression here, Hx is equal to minus summation Px log Px, and look at what is below the sigma sign. X belongs to support of Px. That means enumerate only those values of x for which the probability is non-zero. Do not enumerate those functions of x for which the probability is 0. And why are we worried about that? Because log of 0 is indeterminate. So, the definition should take care that it does not lead to an indeterminate situation. What is log of 0? Minus infinity. So, you don't want to take log of 0. So, how do you avoid log of 0? By enumerating only those points of x over which it is non-zero. Is that clear? From where is this symbol H coming? It is coming from probably thermodynamics. Remember, thermodynamics also has an entropy function. Huh? Right, right. Of course, some book was casually writing that this H could be for Hartley, because he defined information 20 years back, or tried to define information. But it is primarily from thermodynamics. Okay, what about the next point here? Can somebody help me understand that point? So, what this is saying is, if you look at the summation Pxx log Pxx, so Pxx is multiplied by something, and that something is log Px. So that means it is the expected value of whatever that something is, and that something is minus log Pxx, because expected value of any random variable is defined as expected value of any function of a random variable. Suppose I have a function of x where x is a random variable, then the expected value is defined as summation whatever is the probability of x into that function x. So, this is a straightforward application of what we do for the expected value of x. So, the uncertainty or entropy of a discrete random variable is given by this. Now, please note that the word entropy has been used to denote uncertainty, and information is used to denote reduction in uncertainty. When you reduce uncertainty, so by the amount the uncertainty is reduced, that much information has been conveyed. Joint entropy of discrete random variable x and y is given by hxy. So, this is the joint event xy, expected value of the joint probability function, and because it is again expected value, so you will have this pxy minus log pxy. So, suppose x has two possible values, that means x can take two possible values, small x1 and small x2, and that probability of x1 is p and probability of x2 is 1 minus p, then the uncertainty of x in bits, provided that this probability is between 0 and 1, is given by this function. From where do we get this function? This is just expanding the definition of entropy, pi log pi. So, minus pi log pi. So, first event has probability p, that is why it is p log p, second event has probability 1 minus p, so 1 minus p, 1 minus p. This above expression is known as binary entropy function and is denoted by Hp. It is this function that we were denoting as the function that has to be continuous, the p log p. This is a very important function, and so we plot it here. This is the figure of binary entropy function. So, we see that as you keep on changing the value of the small p from 0 to 1, it keeps on changing. First it increases and then it again decreases. So, it has only one maxima, and where that maxima takes place, p is equal to half. How do you say this is intuitively satisfying or not satisfying? Satisfying, because the maximum uncertainty is when both the events are equally likely. If one event was more likely, then uncertainty is less. If both the events are equally likely, uncertainty is maximum. So, that is something very beautiful, that whatever we are doing, we are trying to make our mathematical framework more rigorous, more structured, but every time we are testing it against intuition, and that in that sense it is reinforcing our thoughts about uncertainty. Now, this is a very useful, very productive, very popular inequality used across information theory. So, it says that if you have any positive real number r, then log of r is always upper bounded by r minus 1 log of e. Log of r less than equal to r minus 1 log of e, with equality if and only if r is equal to 1. That means at only one point equality occurs, and that point is when r is equal to 1. In fact, this curve looks like this. See, the right hand side, if you look at the r minus 1, the r minus 1 actually crosses, it is a straight line. I am plotting r minus 1 here, and if you plot this log r, then this log r is like this. So, they touch each other at this point r is equal to 1. This is the point 1, and this is of course r. And so, log r is always less than or equal to r minus 1 log e. How do you prove this? Of course, graphically it is easier to see. Proof is also not very difficult. It is saying that if I differentiate this, I get 1 by r. This 1 by r is greater than 1 whenever r is less than 1. It is equal to 1 by r which is less than 1 whenever r is greater than 1. So, the graphs can never cross. Why the graphs can never cross? Because r minus 1 is equal to here. This is straight line is r minus 1. So, at one time its slope is more, but slope is more before it meets. After that the slope is less. So, that is why the graphs can never cross. So, this is used as a proof of this, and please remember, just memorize this. This is very useful. In fact, even in today's lecture we will be using this. The log r is less than equal to r with equality if and only if r is equal to 1. Multiplying both sides of the inequality by log a, noting that log r is equal gives the desired inequality. Okay. Now look at some properties of entropy. So we want to cover some landscape. In that landscape, we want to touch the important concepts of entropy. We have already introduced entropy. We want to introduce conditional entropy. We want to talk about mutual information, right? Mutual information is something that is very, very important from communication point of view. So we want to reach to mutual information. For that, the road is via conditional entropy. So before that, let us talk about one or two properties of entropy. It says that if a discrete random variable has L possible values, then this entropy is lower bounded by 0 and upper bounded by log of L. And when will the upper bound occur? Upper bound occurs only when all the L values are equally likely and their probabilities are same, that is 1 by capital L. Proof is very simple. I do not think we need to spend time on this. It is very that if you put Px is equal to 1, naturally it is 0. If Px is between this, then naturally this is a positive quantity. So Hx is equal to 0 if and only if Px equals 1 for every x, but there can be only one such x. So if any one x has probability 1, that means there cannot be any other x which has probability 1. Okay, now this is the first application of the IT inequality. What is the first application? That this result will be proven using the IT inequality, and here is the IT inequality. So you start with this left hand side, that is take log L to the left hand side, so define Hx minus log L. This is from the definition of Hx minus log L, take log L inside, right. So we take log L inside, and because this Px is over the support of x, this is equal to 1, so there is no problem, I can easily take it inside. I can merge these two because both are log functions, so because it is minus sign, it will come in the denominator. So first three steps are straightforward, that is why it is equal to sign. Now the moment I see a log function which is in compact notation, I replace it by r minus 1. What is r? This is r, 1 upon Lpx. This is 1 upon Lpx minus 1 into log of E. Here this one? Okay. So because log L is being multiplied by summation over Pxx, what is the summation of Pxx? 1. So I can take it inside. It does not change anything. No, it is not, minus is here. Here. Huh? Huh, so that is why it is 1 by Px, na? 1 by Px. Right. Right. And then look at this log, and now this is that log r, whatever was r on the previous slide, that was multiplied by r minus 1 log E. Now the moment I do this, Px cancels, I get 1 by L, and this is equal to minus Px log E, but this is equal to 1 minus 1, this is equal to 0. So that means Hx minus log L is less than or equal to, there is a equal to sign, I hope it has come in the printing. This is not less than, this is less than equal to. Please add equal to there. So Hx minus log L is less than equal to 0, that means my inequality is proven. So Hx is less than or equal to log of L. So that means we are not only able to lower bound Hx from 0, but we are also able to upper bound Hx, that it is cannot exceed capital L. Yes, sorry.
From the first line, we are coming to second one. So Pxx term is not there in the second one, the log L.
Right.
So how it came with log L?
Right. So that is what we are saying, na, that because summation Pxs is equal to 1 and log L is independent of x. Less than or equal to. No, here it is equal to. This is equal to this. So this step is equal to this. So now we are saying finally compared to the left hand side, because we introduced this less than equal to, so that less than equal to is dominating here. Okay, this is very simple, so I will not waste time here. This is just conversion of logs, so we will just skip over this. Okay, coming to conditional entropy. The conditional entropy is given that if you know that an event y has occurred, now sometimes knowing that the event y has occurred may reduce the uncertainty about x if they are correlated, right. If they are not related, fine, it will not reduce, but that is why we are defining conditional entropy. That means how does my uncertainty about an event changes if I know outcome of some other event which may be possibly related to this event. That is what is conditional entropy. So, Hx given that capital Y is equal to y. So, again following from the definition minus Pxy given log Pxy, and again expectation, that comes out to be this. Similarly, this was for a specific event, we can define it more generally. The conditional entropy of the discrete random variable x given the discrete random variable y. So, here we are not saying a specific y, we are saying in general y is known. So, that then we define it as Hx given y. Both of these are conditional entropies. In one case we are saying that the outcome is a specific event, in the second one we are saying outcome is known. And then we define it in the same manner as earlier. So, what is the important concept? Important concept is that there is a need to define something which we will call as conditional entropy, and that something will be conditioned on the availability of information about the event y. Okay. Now, there is something called information divergence. Don't bother too much about the size of the word information divergence. It is not a complicated concept. It is basically also known as relative entropy. So, what it is saying is that if I have two distribution functions, suppose I have a random variable x with some distribution and I have a random variable y with some distribution. Suppose both of them are over the same support set, say x1 to xn and y1 to y1, and both are same. Now, in this case, can I define what is the distance between these two probability distribution functions? And because this concept is also useful in statistics, so it has multiple names. In fact, in statistics literature it is known as Kullback-Leibler measure. Here in some books it will be relative entropy, sometimes it will be known as information divergence, but essentially it is, the symbol is these two parallel lines. So, Px parallel lines Px hat, that means it is trying to find out the distribution between the distribution function of x and x hat, and it is defined like this: Pxx log of Pxy divided by Px hat. So, suppose that x has L possible values, let x hat have the probability distribution 1 by L for all x, then this is equal to expected value of this. Why it is expected value? Because of this function Pxx. So, whatever is after Pxx, it is the expected value of this function, expected value of log of Pxx divided by Px hat x hat. When you have taken this as 1 by L, that means equally likely. So, this becomes 1 by L. So, that L comes in the numerator, that comes outside, and so log L minus Hx. Now, you can see that whatever was information divergence, in this special case it reduces to some familiar expression. Why we are calling this familiar expression? Hx minus log L we have already seen. We have already seen Hx is upper bounded by L. So, what can you tell me about this? This quantity will always be greater than or equal to 0, and in fact that is why it is known as distance measure. Distances are always known to be non-zero. Why am I saying it is always greater than 0? Is somebody wanting to know that? Because we have already proven that Hx is upper bounded by log L. Of course, this is in a special case, we will prove the general result later, but this is a special case. Oh, now this is the general result, and this is the proof for the general result. So, the previous slide was about the special case was x hat is equal to 1 by L. Now, here is the general result: divergence inequality for any two probability distributions P and Q on x, it is always positive, and again we use IT inequality. So, here this is log whatever is that R, we substitute that by R minus 1 log E. Can you see that? So, equal to has been replaced by less than equal to, and this Px cancels, you get only Qx, summation of qx is equal to 1, here px summation again equal to 1, so you get px log e, 1 1 cancels, this becomes 0. So already we have seen two applications of the IT inequality. Wherever you get that log of some quantity r, where r is the number, real positive number, just replace that by r minus 1 log e. True, true, true. Now I am introducing this very, very important concept. In fact, especially from the communication point of view, mutual information carries a very, very special place, and I will come to that why it carries a very special place. Before that, let me tell you what is the quantity that is defined as mutual information. So the mutual information between the discrete random variable x and y is this quantity. So this is the joint probability. I hope you understand the word joint probability, right? So pxy x comma y, log of this joint event divided by as if it was the product of the two events, that is pxx into pyy, right? Marginal probabilities when you take the integration with respect to 1. This can be written using base probability. This can be written like this, and then I can take the log of the two functions outside. So log pxs is the denominator, I can take it with the minus sign outside, this remains with the plus side outside. What is here is that this reduces to pxx log pxx, if I do the summation over that only, right? And here this is doing the summation over x comma y both. This belongs to what is a familiar definition, that is hx, and this is again a familiar definition, that is conditional entropy. So if you do not want to focus on the maths, you can for the time being skip the maths, but focus on ixy is equal to a function of two entropies. What are the two entropies? Entropy of x minus the conditional entropy of x given y. And why is mutual information very, very, very important? Because mutual information will lead us to that number which we started with the very beginning, that number which we said above which information rate cannot go. For any communication channel, we said that if the information rate is below a number, capacity. So if I compute the mutual information between what is fed into the channel and what is received at the other end of the channel, what is the mutual information between the two, and what is the maximum mutual information that they can have, that number is the capacity of the channel. So essentially all capacity exercises reduce to trying to find out the maximum possible value of the mutual information. Okay, we will come to that. The mutual information between the values x and y, that we have already seen this hx minus hx given y. Now we will see this slightly more. So the joint event xy is the entropy of x and the entropy of y given x. In other words, it can also be written as entropy of y, entropy hx given y, and this implies that hx minus hx given y, because if I equate this to this, so hx minus hx given y will turn out to be the same as hy minus hy given x. And what is this? This is ix colon y. What is this? This iy colon x. So what is this slide trying to say? This slide is trying to say that as expected, the mutual information of x given y, x and y is the same as the mutual information of y and x. That is, it is symmetric as expected. I x colon y is the same as I y colon x. How did I write this? Any discussion on this? So here the uncertainty in x y is equal to the uncertainty in x plus the uncertainty in y given x. No, this is not the joint entropy. This is the entropy of xy. There are two random variables, right. So, the entropy of xy is equal to uncertainty in x plus whatever the remaining uncertainty in y after given x. With this, another way of writing this is that entropy of y plus the entropy in x given y. This has already been proven. Sorry?
H of xy is equal from where we go?
This one, na? So that is what I am explaining, okay. So suppose x and y are independent, then what is hxy equal to? Correct. Now if x and y are not independent, then hx plus hy given x. So that's what we are saying, hx plus hy given x, or in other words I can say hy plus hy given x. By the way, if you have a doubt, you can verify this mathematically also, because you know the definition of conditional entropy. Please take it as an exercise. Please verify this formula from the basic principles, because you know both the definitions. We have already discussed the definition of conditional entropy, we have already discussed the definition of unconditional entropy. Substitute the two formula, and again, as I have said this earlier, intuitively satisfying result that the uncertainty, if x is told, then the remaining uncertainty is only y given x, if the total uncertainty of the event xy is there, right.
So first we have taken the uncertainty of any one of them.
Right.
So what is left? We are adding that.
Correct. Exactly.
Doesn't matter whether it is x or y.
Exactly.
It will come out to be.
Exactly. That is what we are saying, and this can also be verified from the definitions. Okay. Now here we are saying that for any two discrete random variables, can you prove that the conditional entropy, that is hx given y, is always less than or equal to x hx with equality if and only if x and y are independent random variables. How do you prove this? So let us start with the expression for mutual information. This is the expression for mutual information, and again you will have to do this as an exercise. I am not going to spend time here. Using the expression that I have already discussed for relative entropy or the information divergence, you can show that mutual information is nothing but the information divergence between these two density functions, px comma y and px into py. We have already shown that information divergence is greater than or equal to 0. So this is a one line proof. So because this is information divergence, because this is greater than 0, that means hx minus hx given y is greater than 0, and so this is established, that is hx given y is always less than hx. Again intuitively satisfying, because if there is some uncertainty about x, the uncertainty of it given y can only be less than or equal to that. right. So if there is some uncertainty about x, and if I compare that the uncertainty in x given y, certainly the second one cannot exceed the first one. It can at best be or at worst be equal. When they are, and when will that be equal? When they are independent. Okay, now we want to do a numerical example. Please read this question. So this question has two steps. First, there is a die, right? We are rolling a die, and if the face of the die is 1 to 4, an unbiased coin is tossed once, and if the face of the die is 5 or 6, the coin is tossed twice. So we have a die, we roll the die. If we get 1 to 4, I will toss a coin once. If I get the outcome as 5 or 6, I will toss the coin twice. Find the information about the face of the die by the number of heads obtained. Now if you are told that 2 heads were obtained, or 1 head was obtained, or 0 head was obtained, from that information tell the information about the face of the die, right. So let us do it. So let x be the random variable that denote the face of the die, let y denote the number of heads. What will what is the value x can take? It can take only 2 values, x1 when face of the die is 1, 2, 3, 4 and x2 when face of the die is 5 or 6, because the outcomes are different only for these two situations. Y takes 3 values, y0, y1, y2 depending on whether there are no heads, one head or two heads. How can there be no heads? Right. So what happens is that both the times it is tail is coming. And of course remember that in the first case the coin is tossed only once. Now since the die is unbiased, this step is very easy. Probability of x1 is 2 by 3, x2 is 1 by 3. Why? Because this is 4 by 6, 4 by 6 is 2 by 3 and this is 2 by 6, that is 1 by 3, correct? Coin is also unbiased. So what is the probability of the coin given x1 and given x1? Probability is equal to half. And what is the probability of y2 given x1? Oh, why this is 0? Two heads cannot come when you toss it once. If you have tossed it once, how can you get two heads? So that is why the probability of two heads when x1 is true is 0. Agreed? Similarly, you can find out the probability of y0, y2 and y1 for x2 just like you found for x1, similarly for x2. And then we can find out the probability of y0, y1, y2. And now we can find out the entropy or the uncertainty in the random variable y. It depends on three probabilities. We have computed the three probabilities: 5 by 12, 1 by 2, 1 by 12. So 5 by 12, 1 by 2, 1 by 12. So apply minus summation pi log pi, minus summation pi log pi, right? You know all the three pi's, and now this is telling me that how much uncertainty is there in the random variable y. I hope you know how to find out p y naught. So multiplied by the probability of x1 multiplied by the probability of x2, based on that you can find this. I am sure if you have difficulty, some of your friend can help it. Now find the uncertainty in y given x. Go from the definitions, hy given x1 and hy given x2. So hy given x1 we have already computed, half 0, remember the last line on the previous slide, and then here 1 by 4, half 1 by 4, that is 1 by 4, half 1 by 4. So this is here. These are the two uncertainties, and px1 is 2 by 3, px2 is 1 by 3. We compute this and we get hy given x is 1.167. So what is the mutual information between x and y? Subtract from hy given x. And as expected, we are getting a number which is more 0 or more than 0, and that number here turns out to be 0.158 bits. So if you are told that how many heads the coin has, the information that you have about the face of the die is 0.158. Now this is the power of measuring information. Before this framework, before this model, there was no way of computing such a number. We knew that I had some information. If the coin is ahead, I have some information about what was the face of the die, but I had no way of quantifying it, no way of putting a number to it. And this is a very consistent framework because it is satisfying all our intuitions. In fact, I would say now go back and repeat this exercise for different situations, and in every situation you will see that it will support your intuition. In the shortage of time, I think I have to go slightly faster. Please allow me to go slightly faster. Oh, I think I will skip this. So these are 3 slides. I will just tell you one important equation in these slides, and then you can study on your own. This is the only equation that all the next 3 slides rely on. That is, the joint probability of events x1 to xn can be written as the product of conditional probabilities. And what are those conditional probabilities? It says product I is equal to 1 to n p xi, and then subtract from xi minus 1 to x1. So this right hand side is looking like this: product of x1 into product of x2 given x1 into product of x3 given x2 x1 and so on. So what is this called? Chain rule. This is the chain rule of probability, that is why the slide heading is chain rule. So just mark this, underline this equation, and once you understand this equation, the remaining things follow. So what we are saying is that because these probability distribution functions have a chain rule, so naturally it corresponds to a chain rule in terms of both entropy and mutual information. So the next slide is about entropy, and then is about the information divergence. Any quick question? Yeah.
Is there no measure of information for the cases when the x is continuous at the
No, it's there. All that is there. So there we go, but naturally it will come later. So these discretes come naturally, but all that is there for continuous also. Okay, now this brings us to channel capacity. The most important channel, or I should say the important in terms of both starting this topic as well as in terms of its utility, is the discrete memoryless channel. So as the name implies, this channel does not have any memory. What does that mean? Let us see. So within that there are some dispersive channel, focusing channel, symmetric channel, strongly symmetric channel. Don't be intimidated by these names. These names are very, very simple definitions, and in fact even if you don't know those definitions, that is not very important. What is important is to understand the DMC and then the related binary eraser channel and the binary symmetric channel. So it will have an input alphabet A, it will have an output alphabet B. Why? Because it is a discrete channel. How do you say that it is memoryless? It is memoryless because probability of yn given all this depends only on yn given xn. So it has no memory, it does not depend upon xn minus 1, xn minus 2, all those things. And DMC without feedback, that means it does not even depend upon the y's. So here it was the output yn, here is the input xn. So if the input xn does not depend on the y's, as you can see on the right hand side, then it says DMC without feedback. And here this is the output yn that does not depend upon the previous inputs. So that is because it is the memoryless channel. So if it does depend on previous 10 inputs, then of course it is not memoryless. This is for a discrete memoryless channel without feedback. Yes, sorry. Okay, for a DMC without feedback, we can say that the transition probabilities, why these are called transition probabilities? Because it is saying that given the input alphabet from x1 to xn, what is the probability that the DMC produces the output string y1 to yn? And we say that this can again be using the chain rule written as the product of the transition probabilities yi given xi. Why we can write it as yi given xi? Because these are memoryless channels. These are memoryless channels. So that is why it becomes a simple product of individual yi given xi. In this proof, again I would say that the simple theory of probability, this property of probability theory is used, and based on that it is there. Now this is the slide that I was referring to earlier. Channel capacity of a discrete memoryless channel is defined as the maximum average mutual information that can be obtained by the choice of Px. That is the important thing, choice of Px. So what this is saying is that your mutual information depends upon what is the distribution that you have for Px. That is why it is a very difficult problem. There are infinite possibilities for Px. Infinite possibilities for Px. This is saying find that Px for which the mutual information is maximum. That I will call as the capacity of the channel. No wonder there are many channels for which the capacity is still not known. Because this concept is mathematically very hard in terms of evaluation. Yeah, please. additive wide Gaussian noise channel. That is an example of a channel. Therefore, that capacity is known, right? And what is that distribution? Now that should be an automatic question coming from your side, that if the capacity of the AWGN channel is known, then what is the distribution of X in that channel? Huh? Yes. So what happens is that if you want to achieve capacity in a additive wide Gaussian noise channel where the noise is Gaussian, then your input source should also be Gaussian. Huh? It's a very special case, it turns out like that, right? So it's a problem which becomes easy. I am not doing it problem here, I am just telling you so that you understand its importance. Why I am telling these things? So that you understand that this is not theory, this is driving real life. This is setting the limits that communication engineers are trying to achieve. So is it clear why this is very difficult to compute? Because this has to be maximized over all Px, and Px are distribution functions. Okay, so because we know that mutual information is given, so it is saying equivalently C is maximizing this expression. Okay, I think we can do that, but here we can pause here. Can somebody tell me here that when we talk of the additive wide Gaussian noise channel, right, we say that it means that the signal is received in the presence of additive wide Gaussian noise at the receiver. What does this translate to, say, in terms of the standard models for channels that we know? Is it a binary symmetric channel? Is it a binary eraser channel? Is it neither? Think about it. I know all of you know are in a position to understand my questions, so hopefully you will be able to answer it. Let me pose the question here. So input alphabet is 0 1, output alphabet is 0 1, right? 0 can go like this, or 0 can be taken as 1. 1 goes as 0 and 1 goes as 1, right? Suppose this probability is 1 minus epsilon, this probability is epsilon, this probability is epsilon, and this probability is 1 minus epsilon. This is the input side, this is the output side. This is what channel is this? Binary symmetric channel. Binary, why binary? Because two possibilities, symmetric, because the transition probability is a symmetric channel. Now I tell you that I have an AWGN channel, and you know that what is the probability of error of the AWGN channel? Some Q function. Suppose BPSK is there. All of you know this expression, yes or no? At least those who are coming from communication background. You know this expression. What is this? This is just this epsilon. It is telling the probability of error. And what is epsilon? Epsilon is telling the probability of error that 1 becomes 0 or 0 becomes 1. Don't you know that in the case of the additive wide Gaussian channel, when you are using binary BPSK modulation, the probability of 1 becoming 0 is the same as 0 becoming 1. So the error is symmetric. That epsilon is known to you. So the AWGN channel is nothing but a binary symmetric channel. I mean, it can be modeled like that. So these channels, the capacity is studied. Of course, I am not trying to reduce the complexity of the problem. I don't get it oversimplified, because when you talk of AWGN channel, the issue of bandwidth also comes into play, right? So for the time being, all discussions are done per unit hertz. That means per hertz of bandwidth. So that bandwidth can be suitably factored into it.
You can also model it as a binary eraser channel.
But when you talk of Q, there is no equivalent of eraser. When you talk of the Q function, you say either the bit is received correctly or incorrectly. So you can do that in a different framework. And when you are allowing the receiver to announce to the world that I have not received it correctly, in fact it was blanked out. So that is a sort of a ternary kind of situation. That means 1, 0 and eraser, 3 outputs are there. So, that is why it is called binary eraser channel. So, the model of the story is that these simple models are actually much more powerful than they initially appear. You just need 1-2 steps to be able to relate them to real life. They may convey a picture as if, oh, these are just paper, we are playing games. Actually, they are intimately connected to real life. That bridge has to be built. Okay, this is the uniformly dispersive channel. That means that both 0 and 1, if they are equally, if the probabilities of becoming the two outputs here B1 and B2 and here B2, B3 both are half-half. So, this 0 and 1 are dispersing equally, that means they have the same probabilities of dispersion. So, that is what is the formal definition of uniformly dispersive channel. And so, why we define these channels? Because in these cases we can always define this conditional entropies, and also we can use the definitions of the conditional entropies to be able to find the capacity. So, the capacity for a uniformly dispersive channel can be shown to be this, and again the proof is simple. So, I have given it here. So, this is the capacity of a uniformly dispersive channel. Why is this a very precious situation? Why is this being discussed separately? Because you are always looking for situations where you can actually compute the capacity. It is such a difficult thing that you define some special cases. So, uniformly dispersive channel is one special case where the capacity expression reduces to something which is simpler than the original expression. So, it reduces to this. Similarly, you have the uniformly focusing channel. So, here the DMC is if the probabilities of all the k transitions to an output letter when put in decreasing order is same for all values. So, in the case of dispersive channel, the focus was on the inputs. In the case of the focusing channel, the focus is on the outputs. So, if you look at B1, it has two inputs, one with probability half and with probability 1 by 4. Look at B2, half 1 by 4. Look at B3, half 1 by 4. Look at B4, half 1 by 4. So, all of these are having the same kind of focusing. And again in this case, you can find that what is the p-wise uniformly distributed follows from the H achieved by uniform input distribution. In fact, here you can also compute that what is the maximum over Hy. And the last example that I want to discuss is DMC is strongly symmetric. In this case, it is both uniformly dispersive and uniformly focusing, and in this case again the expression for capacity is known, and that is that log j plus pj log pj, where pi to p1 to pj are the transition probabilities, and which is the input distribution that will achieve the capacity. That input distribution is px is equal to 1 by k. So, this particular input distribution will achieve the maximum mutual information, and it will also achieve the maximum possible mutual information. So, that means it is a capacity achieving distribution. I know I rushed through the last 10 minutes, but that was only in the interest of time. So, yeah, please.
Distribution is uniform, then
Capacity is achieved.
achieved.
Huh.
But the Gaussian channel is also a symmetric channel, you say.
No, so this is a strongly symmetric channel, right?
Symmetric channel,
Huh.
that's what we are talking
Right. So,
about. This is same as the Gaussian channel.
right, I will tell you. So, now look at 2-3 situations. First is, I have not yet told you that this epsilon is what. So, nowhere have I brought here the distribution of the noise. Why am I pointing this out? Because I am pointing out that these are more general models, right. That is the first point. Second point is, all these situations are talking of discrete distributions, right. When you are talking the AWGN channel, in that case when you are saying x takes a Gaussian curve, that is not a discrete distribution, it is a continuous distribution. So, these are the two things which are distinct, so that you do not mix the two. So, here we are talking of discrete distributions, right, and here we are talking of epsilon which is general, right. In the case of AWGN, yes, epsilon can indeed be computed, but in the case of the capacity achieving distribution, this x is a continuous function, and here that is why when you are taking the discrete value, then it is not a it cannot be Gaussian, it has to be equal. So, what is the conclusion of these models? The conclusion of these models is that we distill some simpler models which are special cases of the general model, but at the same time these models can have several special cases from real life when we define epsilon, right. But when we want to go from discrete to continuous, then we will need the concept of differential entropy that we have not done here. So, we are handicapped that we are not discussing differential entropy. Input. So in
Passing through the channel. When you say it is a discrete channel, it refers to time discreteness or
no, it refers to the possible outcomes that it has.
outcomes are discrete.
Right, correct. And one more thing that comes very sort of often, it comes, one is the usage of IT inequality. Second thing that comes often is that many of the times you must try equally likely situation, and equally likely is capacity achieving quite a number of times, like as we have seen here also.
Cover that's not this book.
Huh. Thomas and cover. Huh.
Here and there it says you take 0 log 0 h 0. Actually, very uncomfortable.
So, you use the notion of support, that is why it started by support. So, that will take care of this problem. You take the integration or take the summation over the support of x.
Many places is saying you take it 0, but actually that is not 0.
So, you use the notion of support. That helps. Yeah, please.
Comes to mind that this perspective that you maximize the mutual information by choosing an input distribution.
Correct.
It just makes me think that is that the reason why Shannon said choose a code with randomly chosen code words.
Right.
So the choice of random code words will induce a distribution on an input x.
Right.
Is that perspective?
Right.
That's why we worry about the weight distribution of the code.
Right.
That's the previous lesson.
Yes. Weight is very important. And in case you are really interested, I will just tell you read one thing. 2 hours I could not have done it. One important thing that I have not done, that is typical sequences. Just write that topic. Typical sequences. Right? If you want to, if you have gotten interested in information theory, I hope you have, then please read typical sequences. TYPICAL, typical sequences. Then the story will become even more beautiful. That how it sort of brings in the weak law of large numbers, how it brings in the notion that why some sequences can be assumed to be typical of a situation, and then your random code words will also come into play, that those will be typical, and then they will become capacity achieving. In fact, in these Massey's textbook that I referred, which is on the net, which is available on the net, there is this chapter on typical sequences, jointly typical sequences or just typical sequences. So, right. So, it means per usage. So it says in the discrete sense that if you have chosen one of the symbols, now when this symbol is going, how much information you can convey? It can mean that. It can mean that. Another way of doing it is that if you assume a waveform to be of the Hertz 1 hertz to be having the same as the symbol, then using that you can say per hertz. So, some books will indeed write it as per hertz, some will write it as per usage. Okay, I think I will end here. Thank you. So, this title is Robert Ashe, this paperback is available.